So what we've shown is that the surface integral of this function phi on this surface is exactly equal to 4 pi. And that's the total accumulation of this function on that piece of the paraboloid. So what we want to do is try to generalize some of the ideas that we talked about for line integrals to surface integrals. And we can do that first by defining what it means to be independent of the surface. For certain classes of surface integrals, we're going to see that the surface integral is independent of the given surface on which we evaluate it. And just for argument's sake, we'll draw a general kind of picture of this surface, just to have a nice diagram of what it is we're talking about. So let's say we have some bounding curve C, and C is going to be a bounding curve of a given surface if it's connected to the surface as such. So we say that this is the bounding curve of the surface. And in general, the surface integral of some scalar function is said to be independent of the surface with the boundary curve C of the surface S with the boundary curve C if the numerical value of it is the same for each. So for every piecewise smooth surface with the same boundary curve. And what's nice about this is if this is true, right, so in the case of such dependence, so if a surface integral is independent, which is definitely not always true, then we can choose, or one may choose, the simplest possible surface to evaluate the integral. And this is a very, very nice idea that we is very similar to the idea of whether when a line integral is path independent, we can also have that a surface integral is surface independent of the surface. So this concept of path independence, or independence of the surface integral, we'll see that it relies very heavily, and when we're trying to show things about given integrals, we're going to have to use the integral theorem. So to show independence, for a given integral, we will use the integral theorems. So this is Stokes and the divergence theorem, which will be proven in the subsequent lectures. So moving on, I'm going to finally do what we did in much the same way as we defined the concept of circulation of a line integral, and we use circulation to define work and so on and so forth, or we use the idea of the path integral to define work. For surface integrals, we can also provide insight into how vector fields are behaving. This is in 3D space. Specifically, if we consider our general surface, so we have our boundary curve and we have some surface. So some surface S. We can go through and give a meaning to exactly what the vector field is doing along the surface. So let's say the surface S now is immersed not in a scalar field but in some vector field F. So at every given point along the surface, the vector field F is going to be flowing in some direction. And this could be related to a fluid flow field or an electromagnetic field. But the idea is that we assume that at every point of the surface we have a vector defined coming from this vector field as a function of position. And then we'll also assume that we have a unique unit vector that gives a direction in some individual direction. Now it's important to note this unit vector does not necessarily have to be in any specified direction. but we'll say we have some unit vector field defined on our surface. Well, we can talk about, and we can definitely go through and compute the surface integral over S of the scalar function f dot product with u hat ds on the surface. And this is exactly the accumulation of the scalar function f dot u hat on the surface S, right, or the net accumulation of f dot u hat on the surface S. This is called the general surface integral of the vector field f on surface S. And this is in the direction of the unit vector field u hat. And essentially this value is giving you an idea of the net amount that the vector field f is flowing in the direction of u hat on the surface. Because if you remember that this product, the dot product of f with u hat, this is just equal to the projection of the vector f in the direction of u hat at any single point in the surface. And if you want to look at the magnitude, you can go ahead and look at that. It's the magnitude of f times cosine of theta, where theta is the angle between u hat and u. And notice that u hat in general is changing as you move along the surface. So this is the idea of what the surface integral of a vector field looks like in general. Right, specifically, if you were to evaluate this, you would need to go through and use the parameterization of the surface and take the dot product of that with the unit vector field on with respect to this parameterization, and then it would be ds is the magnitude of ru cross rv du dv on the surface. So this would be the integral that you would have to go through and evaluate. Now, in general, when you hear the idea, the name surface integral of a vector field, typically this u hat is actually taken to be a very special vector u hat, very special direction, and this is the normal direction. So typically, right, what we consider is the surface integral of a vector field f on some surface of f on some surface S is a special case of this general surface integral. We take the surface integral of f on some surface S in the normal direction, or in the direction of a unit vector n hat, where n is normal to the surface. In which case the expression for the surface integral becomes very, very nice. The surface integral of f dot n hat ds can be rewritten using the definition of n hat. And if you remember, n hat was defined to be equal to the cross product of the derivative of the position vector with respect to u in our parameterization. And I'm going to move this onto the next page just to create some more room. Now right here, just to summarize, if we choose u hat to be equal to n hat in this formula right here, then we get the surface integral of f on some surface s in the normal direction to the surface, or in the perpendicular direction to the surface. This picture right here can be redrawn corresponding to directly this situation. Where we simply replace all of these general direction vectors with normal vectors, unit normal vectors to the surface. The normal vector here looks like this. Normal vector here looks like this. Like this. And so on and so forth. So if we take the general definition for the surface integral of a vector field, and we integrate the very special u hat, which is the normal direction to the surface, we get what's generally considered the surface integral. So this is really what the surface integral is and why we're defining it the way we are. But typically when you read about a surface integral, it's almost always going to be a surface integral of a vector field. It's almost always going to be with respect to the normal vector field for some surface. But so if we go through and evaluate this now, and kind of see what this formula reduces to, it's actually going to reduce in a very special way. So in the parametric form, reduces to the vector field on the surface dot product with the unit normal where n hat is the unit normal, which is partial derivative of r with respect to u across the partial derivative of r with respect to v divided by the magnitude of this vector times ds, where ds is the magnitude of dr du across dr dv. And you'll immediately notice that something very nice happens, and we get a cancellation. The magnitude of our normal vector cancels out, And then we have that this surface integral of a vector field normal to a surface is just the vector f, the vector field f at a point r of uv on the surface, dot product with dr du cross dr dv du dv. And this would be how you would go through and exactly evaluate a given surface integral. It's using this parameterization right here. Now, there are other ways of evaluating a surface integral, or other ways of finding a normal vector for a given surface that we'll talk about a little bit later on. But the idea here is that this is how you would use parameterization to go through and evaluate the integral. And you get this very, very nice simplified formula, which only requires you to know the cross product vector and then the vector field on the surface, r of uv. And this is exactly giving you the correct value of this surface integral. And remember, the value that you calculate when you calculate this is exactly the total accumulation of the vector field f dotted with n hat on the surface S, or the accumulation of the normal component of the vector field on the surface S. And this actually has another name. The name for this value is called the flux. So it's the flux, or the amount of flowing the vector field is doing through the surface F. S is the flux through the surface S. Because intuitively speaking, this is the accumulation, or the net accumulation of this vector field normal to the surface. And sometimes we denote flux by capital phi sub s, just to simplify things, to make things look a little bit nicer. But this is exactly what we're getting when we evaluate this integral. And we're going to see that the integral theorems that we've mentioned so far, so we'll talk about the next couple lectures, Stokes' theorem and the divergence theorem and Green's theorem. All of these integral theorems are related to either a relationship between curl and the circulation, or the divergence theorem relates the divergence of a vector field in some region to the flux through the boundary of that region. And these integral theorems are going to really exactly do what we talked about before, which is to generalize the fundamental theorem of calculus to multivariable functions and vector fields. So using this idea of flux, we'll just one of the nice things we can do with this is actually get an alternative definition of the divergence that we'll see is exactly equivalent to our original definition of divergence. And this alternative definition of divergence is directly related to the idea of the flux of a vector field. So suppose we want to define divergence, or the divergence of a vector field F using the idea of flux. or the amount of the vector field flowing normal to a surface. So the divergence of f at any point r in three-dimensional space should be the amount of the vector field f at, or the amount that f is flowing. This should be net amount that f is flowing into or out of the point R. Specifically, into or out of a very small surface surrounding the point R. And it turns out that the correct redefinition for the divergence is the divergence of a vector field f at some point R is exactly equal to the limit as delta v goes to 0 of the closed surface integral over some surface delta s of f dot ds divided by the volume of the region, delta v. And this is essentially saying that if we take a point R and we surround R with progressively smaller and smaller surfaces, and this is why delta V and delta S here are going to 0. So the surfaces get smaller and smaller and smaller. Then in the limit, as these surfaces get super small, the amount of divergence of this vector field is the total amount of flux out of the boundary of this surface divided by the total volume. So it's kind of like, in some sense, like an average. Right? This is saying that this is the limit of the flux out of each one of these surfaces divided by the volume of the surface. And in the limit, as delta V goes to 0, you get exactly the correct value of the divergence at the point R of the vector field. And it turns out that this is exactly equivalent. So we're going to see that this definition is exactly equivalent to, and probably better than our previous definition of divergence. It's more useful in certain ways. Just like before, one of the main reasons that this is more useful is that we can think of it as like a useful approximation tool. So the general idea here is that, right, this difference quotient is like saying the flux of F out, say, through S, the net flux of F through S divided by the total volume delta V. And we can use this as a useful approximation tool. For instance, for a given vector field, and for a small enough delta V and delta S, we have that the divergence of a vector field at some point R is approximately equal to the surface integral, or the flux, through delta S divided by the total volume, delta V. Alright, this only holds for small enough delta V and delta S. They'd be very small because it's exactly equal in the limit as these things go to zero. But as long as this volume and this surface are small enough, this approximation holds, in which case we can use this to approximate flux. So for instance, if this surface and this volume is small enough, then we can rewrite this equation to say that the total flux through this small surface delta S is approximately equal to the divergence of F at R times the volume, the total volume of V that this closed surface S is surrounding. This is a very, very good idea, very, very useful idea, and this idea is definitely going to be useful in the web work. Specifically, I think it's in problem 20 of web work 2. You'll see that this idea becomes super useful, and it gives you a super easy way of going through and evaluating exactly, or approximately what the divergence is, or not the divergence is, what the flux is out of a small enough sphere, which is very cool. But this is where we'll leave off the lecture for today. Thank you very much for listening, and I hope you had a great day.